Welcome to the Deep Dive. Today, we're jumping right into something pretty fascinating, near-Earth objects, NEOs.
Absolutely. And specifically, how we defend our planet from them. Planetary defense.
Exactly. We've looked at a great NASA documentary, Planetary Defenders, plus some recent news and strategies.
Yeah, lots of material.
Our goal here is to give you a fast but solid understanding of this whole field. Expect some surprising stuff.
Our mission really is to unpack the process, how we find these asteroids and comets, how we track them, and what we might actually do if one's heading our way.
Showing the work behind it all.
Right, the dedication, the discoveries, the historical context, all of it.
Okay, let's start with discovery. How do we even find these things?
Yeah.
The documentary showed this real-time excitement around spotting a new PHA, a potentially hazardous asteroid.
Yeah, it's pretty cool. They basically take quick sequences of images, like 4 frames of the same patch of sky.
Like a mini-movie.
Exactly. And software flags anything that moves between those frames against the background stars. That's your potential candidate.
But it's not just automated, is it?
No, not at all. That's the interesting part. The software might flag hundreds of potential movers, but then astronomers have to actually look and verify, is it real? Or just, a satellite flare or some noise.
So human eyes are still crucial.
Definitely. Automation plus expert judgment.
And it's not just the big observatories, right? I liked how they mentioned amateur astronomers.
Oh yeah, their contribution is really valuable. People spending their own time scanning the skies.
Imagine finding one. Being the first person ever to see a new minor planet.
It's got to be a thrill. But for the initial wide-scale searching, the heavy lifting is done by these dedicated wide-field survey telescopes.
Constantly scanning.
Constantly. They image huge areas of the sky, and the technique is clever. They digitally remove all the known stars and galaxies from the image.
So anything left over.
That's moving and wasn't there before. That's potentially an NEO.
Okay, so that's how the initial detection happens.
Yeah.
What's the big picture takeaway from that part?
Well, it's a global effort, constantly scanning. We're doing pretty well finding the really huge ones, the civilization enders.
Over 95% found, I think the source said.
That's right. But the smaller ones, say 140 meters plus the city killers, those are much tougher. We've only found maybe 40% of those.
Okay, only 40%. That's
Yeah.
a bit sobering. So what happens right after a possible detection?
Speed is key. The information, a temporary name, time, location, brightness, it gets reported almost immediately.
Where does it go?
To the Minor Planet Center. It's based at Harvard.
Oh, okay. The central hub.
Exactly. They're like the global clearinghouse for all small body observations. They collect data from everyone, everywhere, and then crucially, they make the orbital data public.
Public, so anyone can see it.
Yep. It's a very open, collaborative process, which
Yeah.
is essential, really.
Why is that so important?
Because one observation is just, well, one point in time. You need more data to know where something's actually going.
Right, like seeing a ball for just a split second versus tracking its whole path.
Precisely. So once the Minor Planet Center puts out the initial data, other observatories jump in to get more observations. More data points mean a much, much better orbit calculation.
Which leads us to figuring out the actual threat, doesn't it?
It does. And that's where CNEOS comes in the Center for Near-Earth Object Studies at JPL, the Jet Propulsion Laboratory.
Okay, JPL, what do they do?
They take all that incoming data from the Minor Planet Center, and they calculate their refined orbits. They project these paths forward, sometimes 100 years.
100 years. Wow.
Yeah, looking for any potential close approaches or, importantly, impact risks with Earth.
And this whole cataloging effort, it was actually mandated by Congress.
That's right. First, for the big ones, a kilometer or more across those potential global catastrophes.
The ones we've mostly found.
Yes, over 95%. Then the mandate expanded down to 140 meters, still big enough to wipe out a city or cause major regional damage.
And that's where we're only at about 40% found.
Correct. So the takeaway is we've got a good handle on the giant threats, but there's a whole population of smaller but still very dangerous objects out there that we haven't found yet.
How does CNEOs keep track of all the new data constantly coming in?
They have automated systems, kind of like digital watchdogs.
Watchdogs.
Yeah, constantly scanning the data feed from the Minor Planet Center. If any new object shows even a small chance of hitting Earth,
An alert goes out?
a rapid alert, yes. And that triggers astronomers worldwide to get those vital follow-up observations immediately.
So telescopes like Spacewatch get involved then?
Exactly. They perform crucial follow-up work to refine that initial orbit, which might be a bit fuzzy at first.
They mentioned the orbital arc in the documentary.
Right. The longer you observe an object, the longer its arc across the sky, the more accurately you can predict its future path. It just tightens the uncertainties.
And they focus on virtual impactors. What are those?
Those are objects where, based on the current data, you can't completely rule out an impact, even if the probability is tiny.
So even a 1 in a million chance gets attention.
Absolutely. Because the consequences, however unlikely, would be so high you have to track them very closely until you can definitively rule out an impact.
Makes sense. Okay, so we've found it, we're tracking it, but knowing just its path isn't enough, right?
No, you need to know what it is, its characteristics.
And visible light telescopes have limits.
They do, especially for really dark asteroids. Some asteroids are, blacker than coal. They don't reflect much sunlight.
Hard to see.
Very. That's why infrared telescopes are so important, especially space-based ones.
Because they detect heat.
Exactly. Asteroids absorb sunlight and radiate heat, and infrared telescopes can pick that up, even from dark objects.
And there's a new mission coming for that. NEO surveyor?
Yes, NEO surveyor will operate in the infrared from space. It should give us a much better inventory of these darker, harder-to-spot asteroids.
The documentary also brought up that comet hitting Jupiter, Shoemaker-Levy 9.
Ah, yes, back in 1994. That was a huge wake-up call, seeing those impacts happen live, basically.
What was the impact of? Well, impact.
It really drove home that these collisions are ongoing processes in the solar system, not just ancient history. And it was a major factor in pushing for the creation of NASA's Planetary Defense Coordination Office.
Shifting from just studying past craters to actively looking for future threats.
Precisely.
And the damage potential varies hugely with size.
Oh, absolutely. Kilometer scale is global. But then you have things like Chelyabinsk in 2013.
That was the one in Russia.
Yeah, only about 20 meters across. Tiny, really, compared to the big ones.
But still caused a lot of damage.
Huge airburst, the energy of a small nuclear weapon, shattered windows over a vast area, injured over 1,000 people.
And the scary part was we didn't see it coming.
Nope. It came in from the direction of the sun, hidden in the glare, undetected.
So Chelyabinsk really underlined the need to know more than just the orbit.
Definitely. Size, composition, spin, all these physical properties matter hugely.
How do we figure out composition? Meteorites.
Meteorites are fantastic ground truth. They're pieces of asteroids that landed here, stony ones, iron ones. They tell us what the parent bodies are made of.
And that matters for impact effects.
Oh, yes. A loosely packed rubble pile might break up high in the atmosphere in an airburst, like Chelyabinsk. A solid chunk of iron could punch right through and dig a crater. Big difference in ground damage.
Okay. Meteorites are clues. What about studying asteroids that don't hit us?
That's where planetary radar comes in. It's an active technique.
Active, meaning we send signals out.
Exactly. Places like the Goldstone Solar System radar transmit powerful radio waves towards the asteroid.
And listen for the echo.
Right. By analyzing the bounced signal, how long it takes, how the frequency changes, the signal strength across the object, you can learn a ton.
Like what?
Shape, precise distance, surface features.
Yeah.
Even how fast it's spinning. You can get surprisingly detailed radar images, sometimes down to just a few meters resolution.
Incredible. Is there a recent example of putting all this together?
Yeah, Asteroid 2023 DZ2 was a great case study just last year.
What happened with that one?
Well, when it was first spotted, the initial orbit suggested a non-zero, though small, chance of hitting Earth later on.
Okay, so the alerts went out.
Yep. Triggered a whole international campaign. Optical telescopes tracked it. Radar got its size and shape.
And composition.
That too. NASA's Infrared Telescope Facility, IRTF, looked at its spectrum, the colors of light reflecting off it.
And what did they find?
Its signature matched aubrate meteorites. Very bright, kind of whitish rock. Knowing that helped refine the size estimate.
And the impact risk.
Further observations quickly showed it was going to miss us safely. But the whole episode was a fantastic real-world test of the whole system detection, tracking, characterization, international collaboration. It worked.
That's reassuring. So we're finding them, tracking them, figuring out what they're made of. Let's talk about defense. What if we do find one on a collision course?
Right, planetary defense strategies, and it's absolutely a global issue, requires global cooperation.
The big one recently was the DART mission, wasn't it?
DART, yes. Double Asteroid Redirection Test. A landmark mission.
What was the basic idea?
Kinetic impactor. Basically, you slam a spacecraft into the asteroid to nudge it.
Just hit it.
Pretty much. The goal wasn't to destroy it, just to change its velocity by a tiny amount.
How tiny?
Very tiny. But if you do it years or better yet, decades, before potential impact.
That small nudge adds up over time.
Exactly. A small change in speed, way out in space, translates to a big change in position years later, enough to make it miss Earth entirely.
So DART proved this works.
It really did. They targeted Dimorphos, the small moonlet orbiting the larger asteroid Didymos. The impact was a success.
I saw the images. It was pretty dramatic.
And the results were even better than expected. They were hoping to change Dimorphos's orbital period around Didymos by maybe 10 minutes or so.
And the actual change?
32 minutes, significantly more effective than predicted. It proved the kinetic impactor concept is viable. It's our most mature technology right now.
Are there other ideas besides just hitting them?
Oh yes, several. Though they're less developed, there's the gravity tractor.
Gravity tractor. Sounds like science fiction.
Sort of. You'd park a heavy spacecraft near the asteroid. Its tiny gravitational pull over a long time would slowly tow the asteroid off course.
Wow. Slow but steady.
Very slow. Needs lots of warning time. Then there's the ion beam deflector, using an ion engine to basically spray ions at the asteroid and gently push it.
Gentle pushing. And what about nukes, like in the movies?
Yes. Nuclear explosives are technically an option, but a very complex one, and a last resort. It's not about blowing it to smithereens like Hollywood shows. No, that could just create multiple dangerous fragments. The idea would be to detonate it at a standoff distance, or maybe on the surface, to vaporize rock. That explosion itself creates thrust, pushing the asteroid, but it's fraught with complications, both technical and political.
So the best method depends on the situation.
Absolutely. Size, composition, spin, and crucially, warning time. How much time do we have?
That seems to be the key ingredient for everything, warning time.
Yeah. It's the single most critical factor. Years, preferably decades, are needed to design, build, launch, and travel to an asteroid for any kind of deflection mission.
And we might need to check it out up close first. Reconnaissance.
Ideally, yes. Send a scout mission first to really understand the target before you try to move it. Know your enemy, so to speak.
Makes sense. So NASA's role isn't just finding them, it's also coordination.
A huge part of it. Coordinating with other U.S. agencies, international space agencies, scientists worldwide, planetary defense has to be a team effort.
And they practice this.
They do. Through these tabletop exercises, they simulate a potential impact scenario from start to finish.
Like the hypothetical Asteroid 2023 TTX mentioned in the documentary.
Exactly like that. They'd walk through a scenario. Okay, we've discovered this object. Initial orbit shows a 1% impact probability in, say, 10 years. It looks like it's maybe 200 meters across, but there's uncertainty. Potential impact corridor crosses these countries.
And then figure out what to do.
Right. What observations do we need? What are the potential damage levels? What mitigation options are feasible within the time frame? How do we coordinate internationally? How do we communicate with the public?
Practicing the decision-making under uncertainty.
Precisely. It's all about preparedness, figuring out the procedures, the communication channels, the decision points before you're faced with a real threat.
Okay, let's try and wrap this deep dive up. What are the main things you want people to take away?
I think, first, the discovery and tracking efforts are fundamental. There are eyes on the sky, the essential first step.
Find them before they find us.
Basically, yes. Second, understanding what these objects are, their size, what they're made of, is just as vital for assessing the actual risk and planning what to do.
And third?
Third, we can do something. The DART mission was proof of concept that deflection is possible with current technology. Kinetic impact works. But it all hinges on finding them early. Early detection, precise tracking over time, and international collaboration are absolutely paramount. None of this works without those pieces.
So from spotting fate-moving dots to smashing spacecraft into asteroids, it's quite a journey. Hopefully this gave you a good shortcut to understanding this whole complex and really important field.
Yeah, hope it connected some dots for you. It's a fascinating intersection of science, engineering, and, well, protecting our home.
Yeah, definitely. Yeah. And maybe a final thought to leave you with. As our ability to potentially nudge asteroids grows, how do we as a planet prepare for actually making those decisions if a real threat emerges? How do we ensure global coordination and avoid, panic or conflict when the stakes are so high?
That's a big question. It involves science, policy, communication, a lot to think about.
Indeed. And if you want to dig deeper yourself,
check out the Minor Planet Center website or CNEOs at JPL. Lots of data there. And definitely look up more info on the DART mission. It really is a cool story.